Dear students, I would like to welcome you to our third exercise. Today we are talking about the ceiling of an indoor swimming pool which collapsed many years ago. And there will be also today then a second part where I myself investigated another indoor swimming pool, and we will see the difference of the two materials used. Now, don't be shocked when you see that kind of slide. This is an indoor pool in Uster, nearby Zurich, which collapsed in 1985. And you see here the whole ceiling, which was underneath of the main ceiling, made of concrete, collapsed and fell down. And you see already that due to this collapsing, 12 people died swimming there, and 19 were injured. And have a look at the time. It happened at 9:25 at night, and it was supposed to close at 9:30. So 5 minutes decided of being dead or alive. It's really a tragedy. Now it's clear when this kind of big accident happens that it has to be investigated very carefully. And you see now the following has to be done. First, the information of the system, the history of the indoor pool. It was already 13 years old. And now the mechanical loading, it's very important. We all the time talk about this. The mechanical loading, I have to tell you that this concrete ceiling, which you see here on this 50 meters pool, was attached by these kind of steel bars, steel hangers. And it's clear that these kind of steel hangers, what kind of mechanical loading is on these steel hangers? Think carefully. It's quite easy. When it's attached here on the top ceiling, and then there is a down ceiling, it's just tensile, tension, stress, static. Now the construction, as I told you, it's a concrete ceiling what we see here. And the concrete ceiling, we have to ask ourselves, because we want to calculate the stress in these steel hangers, what is the weight of the concrete ceiling? What do you think? What do you guess? I remember students in former times, they were guessing, some said maybe a few hundred kilograms, or maybe 1 ton, or maximum 2 tons. They are all wrong. The weight of the ceiling was originally 166 tons for a thickness of 8 centimeters, about so thick. So that's enormous weight which is here. Imagine 166 tons. This correlates to about 4 big heavy trucks hanging there on these steel hangers. And now the amount of steel hangers, the number of steel hangers, I have to tell you, that is then the weight after, later on, because people were thinking, oh, the concrete doesn't look so nice, we add additionally a wooden ceiling underneath, and then the thickness was even was getting higher to 92 millimeters, and additionally the weight of the wooden ceiling and the design made it to 215 tons. And all this was now attached by 207 steel hangers. 207. And now you clearly, from that amount of weight and the steel hangers, you can calculate then the stress. And the material used, the architect was thinking, oh, I'm doing something very good. I make it perfect and also relatively expensive. The architect decided to use a so-called stainless steel. This is a German designation. We see here X2. X means it's highly alloyed, and 2 is a number for the content of carbon. So it's a low carbon, 0.02 carbon content. Then 18, that means 18% chromium and 8% nickel. Of course, we know due to this alloy, the steel is then austenitic, and it should be against corrosion, protected, should be. And that's the American designation, 304. Now to calculate again the stress, we need of course a diameter of the steel hanger, and the diameter, you see, it's very small, it's 10 millimeter diameter. Now the calculation of the stress is easy. The stress on one steel hanger is sigma is 187 megapascal. This value we have to compare now with the stress strain curve of this material. You know the stress strain, you have the stress, you have the strain, and then you have the elastic curve, and then the plastic part. Now imagine, what is the elastic limit which is important for this kind of design, for this material? I can tell you, the elastic limit is 185 megapascal. That's not very good, huh? That's strange, that's even bad, that's irresponsible, because we are above the elastic limit already at the beginning of our construction. We are already slightly plastic deformation may occur. And this is also shown, there is a rule, a safety coefficient according to the Swiss architect regulations, and you see the numbers, 1.31 first for the original concrete one, and later on the number even was lowered due to the wooden ceiling, 1.27, and the standard minimum limit is 1.8. So we are already far away from the design, from the pure mechanical loading under the standard limit. We keep in mind that values. Okay, now it's clear what kind of investigations we will perform, and it's clear we have to check all these 207 steel hangers very carefully, what happened, because they are obviously responsible that this kind of ceiling crashed. Now we can tell you, this is first a visual inspection of the steel hangers, and 108 of the 207 were broken. The rest was just teared out. Of course, then there's a high overload on that. Now when we watch at these 3 steel hangers, 2, you see very clearly, they are here in this area heavily corroded, also here in that area. And there were some, there I can tell you, they were located at the corner of the pool area on the top. They showed this kind of appearance, this kind of behavior. When you see this kind of steel hanger, it looks a little bit like when you make a tension test in the laboratory with a specimen. You see very nicely here the necking of the material due to the plastic deformation, and the fracture area has an angle of about 45 degrees. So that was unaffected. And these are very much affected by heavy corrosion. There is some small parts where there was no corrosion, and you see there also the overload fracture, which has also an angle of 45 degrees. And you see here also, here is no necking, and here maybe a little bit necking, but here you see it clearly the difference. So that means they are more or less brittle. The 94 were brittle, and the rest, 14, only a minor part of the steel hangers were fractured ductile. Now I can tell you here to make any analysis of the fracture surfaces doesn't. It's too much corroded. You see nearly nothing in fractography. So we immediately pass over to metallography. Metallography means that we cut here inside in the material, so we can again, that's all the time the same story, watch inside in the material and also check what is here underneath going on. And now we see something, yes, brittle fracture, heavily corroded. Now look, this is now this cut through in the material. So this is the surface of the material. This is what we see on the top. I come back to this later. And what we see very, very deep, you know, it has a scale of 0.4 millimeter. So very, very deep. It's full of cracks, our material. This is our austenitic material. You see very nicely here the twins of the microstructure. Now when we have these kind of cracks, we all the time ask ourselves, are these cracks transgranular or intergranular? Intergranular means along the grain boundaries or through the grains. And when we make here a little bit of higher magnification, we cannot see this here, of course. We have to go to the crack tip, which are very fine, and especially look at this area. There is a small crack, and you see here the grain. So the crack is passing through the grain. So it's dominated by transgranular cracking. Here also. Cracks are branched and transgranular. Now when we think of this and the appearance, and there's another part which is very crazy, broken. Yes, we immediately, I think you already may guess or know already the failure mechanism when we think of the stress loading, when we think when we see the appearance of these transgranular branched cracks, and secondly, when we think of the indoor swimming pool. What do we know about indoor pools? The water has to be cleaned because it's full of bacteria, and for cleaning, what do we put there inside? Chlorine. Chlorine. And the chlorine, what do we know, is in terms of corrosion bad. It has a bad influence, and we have to find out. So the failure mechanism is stress, corrosion, cracking. So we have stress, we saw the cracks, and we have the corrosion environment. For this, we need 3 conditions. First, the stress, that was our mechanical loading, pure tension. Then secondly, the corrosive medium, most probably chlorine, we will find out. And the third one, now you think carefully. Most of you forget this, because for stress, corrosion, cracking, you know, from the corrosion lecture, we have these 3 circles, overlapping circles, and it's very important to know the third part. And I also will ask this in the examination. The third part is what? You need a material which is susceptible to stress, corrosion, cracking, because not all materials, we see this, are susceptible. So obviously this stainless steel is susceptible. Aluminium alloys, for instance, some copper alloys like brass are very much susceptible to stress, corrosion, cracking. But there is, for instance, ferritic steels are not. Keep in mind that, especially for the second example which we are talking about. Okay. Now the mechanism of crack initiation, it's very important to see. Look, there is again now our metallographic specimen. There is the surface. So you watch here the surface of our steel hanger. And there you see the different spots. And these spots here from outside, you see it already here a little bit bigger than. How do we call this again? This is our corrosion pits. It's very interesting to find out why this mechanism came up, why this happened. First, I will talk with you about something which you already may know about the deformation mechanisms in this kind of material. The deformation in this kind of material, maybe you will think about that there is at high magnification you only would see this, there is slip bands inside. And on these slip bands we do have our dislocations. The dislocations are responsible for plastic deformation. So when their plastic deformation starts, there will be more and more dislocations on these slip bands. And when these dislocations meet on the slip bands, the surface, there something very strange can happen. Before I have to tell you to think again of our relatively high loading on these bars, on these steel hangers. We were already, as I told you before, above the elastic limit. So the chance that there is dislocation movement is given. And now there is something else which you also have to take into account, that these surface of these materials here, for this they are called stainless steel, they have a self-protecting layer. What is the composition of this layer? And you think, of course, of the composition of the stainless steel. What did we say? It's a chromium-nickel steel. So it's mainly chromium. The purposes of chromium is first to make the hardening inside of the material, solid solution hardening. And secondly, that the chromium is used here for this protective layer, and the composition of this layer is chromium 2O3, chromium oxide. It's a very, very thin layer, but it's very efficient, it's self-protecting. However, as I told you, when we do have here these mechanisms of the slip bands with the dislocations, and the dislocations pile up here at the surface, they can destroy this thin layer, because this thin layer is quite brittle. And when this thin layer is destroyed, normally when I scratch here, after, let me say, 1 or 2 hours, it will be self-healing, because we have all the time oxygen available from the outside. But in this case, when there is an environment with chlorine around, then when this layer here is destroyed, the chlorine immediately attacks there before it can make the self-healing. So that is the process before here this pit is coming. So this layer here is destroyed locally, and then later on we talk about how this pit is coming up. But the first point is that this layer is destroyed. And you see again the main reason that this layer is destroyed, because of that high mechanical loading on these bars. It's very important, keep in mind. Yeah, we come back now. Again, you see this now here, our steel bar, you see the diameter, it's 10 millimeter, and you see very nicely here some spots from outside, these pits, and there again our metallographic specimen. Now we see the following. There is a pit, and you see the distance between the pits is relatively high. So what starts here in the pits? An electrochemical reaction. The inside of the pit, there we have anodic dissolution of the metal, and here there is a cathode area where oxygen is reduced, and that means there will be a flow of the electric current from here to here. But since this area is here quite big and this is quite small, we have here a very high density of electronic current. That means in this area the dissolution of the metal takes place very fast, very fast. That's a mechanism of pitting corrosion. That's a chemical part. But additionally, you see, when once this pit is formed, from the ground, from the bottom of the pit, start the cracks now. They are now more pushed by mechanical loading. And the mechanics, you remember again, we were already in this part here in a very high stress level, above the elastic limit. And now here on the bottom of that pit, of that small hole, of course, the stress is even higher. You have a higher stress intensity at this crack, at this hole, and from there then the cracks start inside. So there's both a chemical effect and a mechanical effect together, and they made this. And of course we had a lot of time. We have 13 years available. It's a time-dependent process also. Now the corrosive medium can be checked now clearly. We are now going to the scanning electron microscope. We see very nicely, here is again our surface. Here is a pit now in the scanning electron microscope, and you see very nicely these cracks. And now in the scanning electron microscope we can nicely make by X-ray a mapping for the distribution of our element chlorine. And you will see it very nicely. Keep in mind here these cracks, here and here. Look, the chlorine is mostly here or only in the cracks inside. That's also a very interesting mechanism. Why does the chlorine really follow here in the cracks, and especially at the crack tip, and then going and helping to grow the crack deeper and deeper inside? Why? Of course, at the crack tip the metal is dissoluted, and the metal is dissoluted, that means it's positive loaded. It's iron positive loaded. So we need, for compensation of these positive loads, we need negative loads, and chlorine is negative loaded. That means the chlorine will be pushed here all the time, following inside the crack to the crack tip. It's a continuous process to be at the crack tip. That is a very important process. Keep in mind that. Okay, this we already talked about. Yes, this mechanical part, I told you, the crack initiation, and the chemical part of the enrichment of the chlorine. Yes. Now we nearly come to the end, because we have to talk now also about the construction of the indoor pool. I told you already before, this is just a simple scheme. You have here the top ceiling. This is an underneath ceiling, which by the way, I have to tell you, had not really a real function. That's also really ridiculous. It's funny. So, and there the chloride content was measured, and we measured here the chloride content in the pool area. It was about 2%, and here on the top it was 5%, and I can tell you, even on the steel hangers we partially found amounts of 10% locally. There is also now something coming up. Why? Due to this special design, which was very unfavorable, the chlorine all the time coming up here, it was evaporated with the water, with the water bubbles and the steam coming up. It's relatively hot here. It's about the air 30 degrees. And now think of the winter. And in winter outside it can be, sometimes in winter, at least in Switzerland, -10, -20 degrees. At least there is a temperature difference. And now we imagine, when we think again of these steel hangers here, and the top is attached on the top ceiling, and down is it attached here, and there is free. What do you think will be the temperature of this steel hanger. It will be definitely not 30 degrees. There is metal is a good transfer for heat, also for cold air, for the cold. So that will be colder because it's attached here inside. What does it mean? When you have here relatively warm, humid air and you have cold metal, you can make a very easy test. When you have a shower, and in the shower you have two taps, two pipes. One pipe is cold, one pipe is hot, where you get the hot water and you mix it, and you maybe next time when you have a shower you make a big steam in your shower room, and then you will see where the steam condensates. Of course the steam condensates on the cold pipe, and we have here the same mechanism. This humid air, it's not really hot, but you have the time. It's all the time humid and warmer than this cold metal in winter when it's running. So then all the time the condensation of humid air takes place, and the humid air contains chlorine. So that is a reason why the chlorine is brought there and then is attached there. Now we come here already to the conclusion. The mechanism was finally very fast to understand. The failure of the steel hangers is due to stress, corrosion, cracking. And think of the three conditions for stress, corrosion, cracking. And this use of susceptible material, that is our stainless steel, and we have seen there is an enrichment of chlorine due to the construction of the ceiling. And then we found a thin layer of acidic chlorine polluted condensed water on the bars all the time for 13 years. And the main point for the beginning, the static calculation showed that the stress in the bars was 187 megapascal, so above the yield point. So already plastic deformation could slightly start. So that was already the selection of the material was the first mistake, and the second mistake was in the static calculation for that kind of steel hangers. It was overloaded. So we can really say that was an irresponsible behavior of the architect, engineer to make this kind of mistakes. And the biggest mistake was even that 2 years before the failure, before the breakdown, they once checked there in the top between the two ceilings. Somebody was creeping inside and watching, and they found already 2 years before 2 steel hangers were fractured. But they didn't react. They thought, oh, this may happen, it may fracture and so on. When at this day or next day they would have taken these 2 steel hangers and bring to our laboratory to EMPA, and we would have checked, we immediately would have told you have to shut down this indoor pool, and we would have saved the life of 12 people for sure. But what did they make? They said, oh, it's nothing, no problem. We just make it by repair of welding, by welding. And it was even bad welding. So you see again how important is that people behave responsible and sometimes use also their mind. I get really angry when I see about this. But that was also the reason why then later on the architect was sentenced. Because 13 years before he would have not sentenced, but because of this he didn't have to go to prison, but he had to pay something. Okay, for this first part we conclude now, and again if you have any questions you may contact me. But now afterwards you will immediately get the second part where we investigate another swimming pool, and we can learn a lot for this. Thank you very much.